Well, let's keep going with this finding of the center of gravity with ever so slightly more complicated shapes. Here's a beam that weighs 200 pounds, and it's got a box sitting on it that weighs 800 pounds, and another box. Oh, this one is not square. It's shaped like a triangle. It's a wedge-shaped box, and it weighs 400 pounds. And they're giving us some dimensions to the edges of things, but not to the centers of things. And what we want to do is find the center of gravity of this whole beam with its loads on it. So we'll start by drawing a free body diagram. There's an arrow for each of the boxes, and there's an arrow in the middle for the weight of that beam. And now let's figure out where each of those arrows is located. What we're doing is we're figuring out where is the center of gravity of this box, and the center of gravity of this beam, and the center of gravity of that box. Now, for finding the center of gravity of a rectangular box, that's fairly straightforward. You might remember that its center is just halfway across the full width of it. So if it's what is that box? A 6-foot wide box, the center is 3 feet over. So that's fine. What if the box is shaped like a triangle, though? A good thing to know is that for any right triangle, the center of the thing is always 1/3 over and 1/3 up. So if this were a 6-foot wide triangle, its center would be 1/3 of that. It would be 2 feet over. So we can use that to figure out where is our center of gravity for our wedge-shaped box. Thinking about these, so let's see, the center of the 800-pound box, we're going to have to do a little arithmetic. It's 7 feet to the edge of that box. And how far is it to the middle of the box? If the whole box is 6 feet wide, then the middle must be 3 feet over. So the middle of that first box must be 7 feet plus 3 feet is 10 feet. The middle of this beam, well, that's just half of 30 feet, so it must be at 15 feet. How about this wedge-shaped box? So it's 18 feet to the edge of that triangle, and then it's a 6-foot wide triangle. Its center is going to be 1/3 of that distance over. So 1/3 of 6 feet is 2 feet. So it's 2 feet from the edge of the box to its center. 18 feet plus 2 feet takes us to 20 feet to the center of that wedge-shaped box. So here is the free body diagram with those distances filled in. Now we're looking for the overall center of gravity, so let's figure out stuff about the resultant. How heavy is the resultant? Well, the weight of the 3 loads equals the weight of the resultant. There are the weights of the 3 loads, and I've written the sum of all forces in the y direction, because these forces are all coming in the y direction. So if we just add up those 3 forces, that will tell us how heavy the resultant is, and they add up to 1,400 pounds. So there we've added 1,400 pounds to the resultant arrow. That's how heavy it is. Its weight is equal to the weight of the 3 loads. Okay, now let's figure out where this resultant is. The moment caused by the resultant, since it has the same net result as those 3 loads, the moment caused by the resultant equals the moment caused by the 3 loads, as I've written here, using our moment equals force times distance, of course. So let's figure those out. The moment caused by the resultant is negative 1,400 pounds times the distance. We don't know what that is, so we'll just write x. Then these 3 loads, We've got negative 800 times 10. We've got negative 200 times 15. And we've got negative 400 times 20. So I'll just string those all together there. Now we can take our calculator and start simplifying these numbers. So we're left with 1400. Oh, and I multiplied everything by -1 to get rid of those negative signs. So we've got 1400x equals these three numbers, 8,000 plus 3,000 plus 8,000. Adding those up, we've got 1400x equals 19,000. Alrighty, let's find x. We'll divide both sides by 1400. The 1400s can cancel out, and we're left with x equals 19,000 over 1400, which is, when you get out your calculator, 13.571 feet. So where is that center of gravity? It weighs 1,400 pounds, and it is located 13.571 feet from the end. Let's go on to the next set of questions. I drew a couple of these loads, funny shapes, just to make the point that these loads don't have to be rectangular or wedge-shaped. They can really be any shape. Each one's center of gravity just goes through its center, so being a funny shape is no big deal. Here we are. We have a beam that weighs 12,000 pounds, and that beam is 42 feet long. And it has 5 loads sitting on top of it. Here are their weights, and we're going to find the center of gravity for that beam. First, we'll draw a free body diagram. And let me just say, I admit I'm kind of partial to trailers and with axles, but I didn't need to draw it this way. This could totally be a beam in a building or a bridge, and we're looking for the center of gravity for that bridge beam. I just put wheels on it because I like them. Anyhow, so here's a free body diagram with an arrow through the middle of each one of those loads and an arrow in the middle of the 12,000 pound beam that they're sitting on. So let's figure out where they are each located. Well, these are relatively straightforward. You're going to the middle of each load. So this first load is 12 feet wide. Its middle must be 6 feet over. The next funny shaped load is 4 feet wide, so its middle must be 2 feet plus 12 feet. It must be located 14 feet from the end, and so on and so forth. So here are our distances all filled in. Let's figure out where the center of gravity is, first by finding the weight of the resultant and then the location of the resultant. So how heavy is the resultant? The weight of the resultant equals the weight of the 6 loads. And there are the 6 loads, which includes the 12,000 pound beam, and they add up to 38,000 pounds. So that means the resultant must weigh 38,000 pounds. And there we've filled it in on our drawing. Where is it? Well, since it has the same net result as those 6 loads up there, the moment caused by the resultant is the same as the moment caused by the 6 loads. So let's just chug through them. The moment caused by the resultant is force times distance, so 38,000 pounds times, we don't know the distance, so we'll just write x. And then we'll chug through all these 6 loads. 5,000 times 6, 4,000 times 14, so on and so forth. Da, da, da. That's a long string of parentheses. and they're all negative. Everything's negative because they're all clockwise moments. But now we can multiply everything times -1 and get those negative signs out of there. And now let's figure out where x is. Where is that center of gravity located? So 38,000x equals, and here we can take our calculator and start boiling down, start simplifying these sets of numbers. So there, I've done that. And now we can add these all up. Here I've gotten rid of the negative sign. So the moment caused by the resultant, 38,000 times x, equals the moment caused by these 6 loads, and if you add all these up, they add up to 851,000 foot-pounds. Big number. All right. So the moment caused by the resultant equals the moment caused by the 6 loads. The moment caused by the resultants we just saw was 38,000x foot-pounds. The moment caused by those 6 forces, we just added them all up and we found 851,000 foot-pounds. Okay, so we want to get x by itself, so we'll divide both sides by 38,000. The 38,000s cancel out, and x equals 851,000 divided by 38,000. And if you get out your calculator and divide those, you'll find out that x equals 22.395 feet. It's totally fine that it's an odd number of feet. We don't care. That is where it is. So that's where our center of gravity is located. It weighs 38,000 pounds. It equals the weight of all those 6 loads. And it is located at 22.395 feet. There's our center of gravity.